Tonight, I want to show you a structure so large that the word big stops being useful. Not a planet, not a galaxy, not even a supercluster. This is a pattern in space, a connected architecture of galaxy clusters, stretching so far that if you could travel at the speed of light, you'd spend over 1 billion years just crossing it. And here's the strange part. We can't see it like a photo. We detect it the way you detect a city at night from an airplane. By the glow, by the hidden connections, by the way matter gathers where gravity is strongest. Astronomers found it through X-ray fingerprints from hot gas in galaxy clusters, and the structure looks like knotted cords. So they named it Quipu, after an ancient Incan system of tied strings. By the end of this journey, you won't just know a new cosmic fact. You'll feel what it means to live inside a universe built like a web, where emptiness matters as much as everything that shines. The human brain is very good at certain kinds of distance. We understand perfectly what a 10-minute walk feels like, or a few hours behind the wheel. Our brains evolved to survive in spaces our eyes could easily overlook. But the universe, it wasn't built for human yardsticks. Forget about kilometers. Even our solar system, a place light takes hours to cross, is nothing more than a tiny puddle in a vast ocean. Our galaxy, the Milky Way, spans 100,000 light years. At this scale, your intuition simply short circuits. At this point, the numbers stop feeling concrete. And that's exactly where astronomy changes the way it measures distance. Instead of kilometers, it uses light itself. A light year is not a unit of time. It is a unit of distance. It describes how far light travels in 1 year, about 9.5 trillion kilometers. Astronomers use light years because nothing in the universe moves faster than light. It gives them a ruler built into reality itself. But the light year does something even more important. It quietly links distance to time. Light does not arrive instantly. It travels. A light year is not just a measurement of space, it is a time machine. In the universe, there is no such thing as now. When you look at the sun, you are seeing the past from 8 minutes ago. When you look at distant galaxies, you are seeing ghosts from billions of years in the past, stars that likely exploded long before Earth even formed. We aren't just mapping objects. We are mapping the ruins of the past. And within this overlapping web of time, a gargantuan structure begins to emerge. Something that doesn't just connect the stars, but connects the very history of the cosmos. Once distance becomes time, the universe starts to feel less empty. Patterns appear. And with those patterns comes something unexpected, a sense of location. We don't usually think of ourselves as having an address in the universe, but astronomers do. They don't define that address with borders or lines on a map. They define it by structure, and more importantly, by motion. We begin close to home. The Milky Way is a vast spiral galaxy, about 100,000 light years across. It holds hundreds of billions of stars, along with gas, dust, and dark matter. The sun sits far from the crowded center, in a relatively quiet spiral arm. Not in a special place, just one ordinary location among many. On its own, the Milky Way already feels immense. But it isn't isolated. It belongs to a small family called the Local Group. The Local Group contains more than 80 galaxies. A few are large and familiar, like Andromeda and Triangulum. Most are small dwarf galaxies, faint and easily overlooked. These galaxies are not scattered randomly. They are gravitationally bound, slowly moving together over billions of years. In fact, the Milky Way and Andromeda are drifting toward each other right now. their future encounter won't be a sudden collision, but a long, quiet merger. Another example of how the universe builds without urgency. The local group itself sits inside a larger region once known as the Virgo supercluster. This was an early attempt to describe our broader cosmic neighborhood. But as astronomers began measuring not just positions, but motions, the picture changed. Galaxies weren't grouped simply by where they were. They were grouped by where they were moving. When scientists mapped galaxy motions across enormous regions of space, they noticed a shared flow. Clusters of galaxies, spread across hundreds of millions of light years, were drifting in the same general direction. That motion pointed toward a distant region of gravitational influence, often called the Great Attractor. The Great Attractor is not a single object you could photograph. It's a region where mass is concentrated enough to shape the motion of galaxies far beyond its immediate surroundings. This realization marked an important shift. Astronomers began to understand that our place in the universe is defined less by where we are and more by where gravity is slowly pulling us. Following these large-scale motions led to a new definition of our cosmic home. They called it Laniakea, a word meaning immense heaven. Laniakea is not outlined by sharp edges. There are no borders you could draw around it. Instead, it is defined by flow. Galaxies within Laniakea move along gravitational pathways, gradually drawn toward the same general region of space. Their shared motion reveals the structure itself. In this way, Laniakea is less like a territory on a map and more like a watershed, a region defined by where things naturally move. This perspective changes how we think about structure. In the universe, motion matters more than position. Our cosmic address is not fixed. It is dynamic, shaped by gravity, acting over immense spans of time. We are not standing still in space. We are drifting within a vast, interconnected system that existed long before Earth formed. And this brings a quiet sense of belonging. The Milky Way fits inside the local group. The local group flows within Laniakea. Structure didn't suddenly appear with the largest discoveries. It has been present all along, quietly guiding motion across the universe. And yet, even Laniakea, immense as it is, cannot be the final level. If this is our neighborhood, then it raises a natural question. If this is where we live, what is the largest structure the universe has built? Because even Laniakea is only one thread in something much larger. If galaxies fall into a pattern, what holds the pattern in place? The answer is something we don't see. Dark matter does not glow. It doesn't reflect light. It doesn't absorb light in any normal way. And yet, it dominates the structure of the universe. By our best measurements, dark matter makes up about 27% of the universe's total mass energy content. That doesn't mean it's everywhere in the same amount. It means it shapes gravity on the largest scales. Think of it as an invisible gravitational scaffold, a framework of valleys and hills in space. Normal matter, gas, dust, stars, tends to drift and fall into those valleys, and it likely happened in that order. First, dark matter began to clump under gravity. Then gas followed. Then stars ignited. Then galaxies grew inside the structure that was already there. This is the key idea. Galaxies don't trace space, they trace gravity. You don't need to know what dark matter is to understand what it does. It turns the cosmic web into a map of invisible mass. And once you understand the scaffold, the next question becomes unavoidable. How large can a structure built on gravity really be? Thank you for joining me on this journey through the cosmos so far. If you find these deep dives into the structure of our universe as fascinating as I do, please consider subscribing to the channel. Your support allows us to keep exploring these frontier discoveries together. And now, let's continue our journey even deeper into the vast unknown. Long before Quipu entered the conversation, astronomers had already encountered structures that forced them to rethink the scale of the universe. They were called Great Walls. The name itself sounded dramatic. And at first, the discoveries felt that way. As galaxy surveys improved, scientists began mapping space more systematically. Not just individual galaxies, but vast regions filled with thousands of them. One of the earliest surprises came from the CFA redshift survey. What astronomers expected was a roughly even distribution of galaxies. What they found instead was a long, continuous wall. A dense region of galaxies stretching far across space. It wasn't a single object. It was a structure. This discovery challenged assumptions. If galaxies could organize into something this extended, then the universe was capable of building patterns on scales larger than anyone had expected. Later surveys expanded this picture. The Sloan Digital Sky Survey mapped millions of galaxies with unprecedented precision. And again, large-scale structures appeared. Filaments, clusters, and walls spanning hundreds of millions of light-years. Each new map added confidence, but also raised caution. Because with every increase in survey size came a new temptation, to call something the largest. That temptation reached a peak with claims surrounding the Hercules Corona Borealis Great Wall. On paper, it was enormous. A structure so large that it seemed to stretch across more than 10 billion light-years. If true, it would dwarf everything discovered before it. But this is where astronomy began to slow down. Unlike galaxy clusters or X-ray bright filaments, the Hercules Corona Borealis claim relied heavily on indirect signals and statistical clustering. It was based on patterns seen in gamma-ray bursts, not on continuous physical measurements of matter. The data was intriguing, but it was incomplete, and that incompleteness mattered. Astronomers realized something important in this moment. At extreme scales, size alone is not enough. A structure that looks large in one dataset may dissolve when examined with another. Apparent alignments can vanish once observational biases are accounted for. The universe is vast, but our observations are limited, and those limits can create illusions. This led to a shift in mindset. Instead of asking, "What is the biggest thing we can name?" astronomers began asking a more careful question. What is the largest structure we can confirm? Confirmation meant more than appearance. It meant physical coherence, shared gravitational influence, independent lines of evidence pointing to the same conclusion. This is why later discoveries were treated differently. Large structures identified in surveys near the South Pole, for example, benefited from cleaner sky coverage and different observational angles. They helped refine techniques, but they also reinforced caution. The lesson was clear. As maps grow larger, claims must become more conservative. Calling something the largest is not a declaration of ambition. It is a statement of restraint. By the time Quipu was studied, astronomers were no longer eager to rush toward superlatives. They were deeply aware of how easily size could be overstated. Every new candidate was tested against hard questions. Is it physically connected? Is it coherent across multiple data sets? Does it survive changes in perspective and method? If the answer wasn't clearly yes, the claim didn't stand. This caution didn't shrink the universe. It clarified it. It forced scientists to separate what merely looks large from what truly is. And that is why Quipu matters. Not because it is bigger than everything before it, but because it appears at a moment when astronomers had learned to be careful with the word largest. By the time that word was applied to Quipu, it carried weight. It meant that the structure had survived comparison, skepticism, and the hard-earned lessons of earlier discoveries. And it set the stage for what comes next. Because if a structure of this scale can be confirmed after all that caution, then the universe may be capable of organizing matter in ways we are only beginning to understand. Before we go any further, one thing needs to be made absolutely clear. Quipu is not an object. It is not a solid body drifting through space. It does not have a surface. There's nothing you could approach, collide with, or photograph from a single angle. Quipu is a structure. More precisely, it is a connected network made up of roughly 68 galaxy clusters, linked together across an enormous region of space. When astronomers map it out, that network stretches for nearly 1.4 billion light-years. At that scale, everyday language starts to break down. We are used to thinking in terms of things. Planets, stars, galaxies. Quipu doesn't fit into that category. It is not one thing placed into space. It is a pattern revealed by space. A large-scale arrangement shaped by gravity and traced by matter over time. And it is important to understand what Quipu is not. It is not a random alignment. It is not a chance grouping seen from a particular angle. It is a coherent structure, meaning its components are physically connected by the same underlying gravitational framework. That distinction matters, because when astronomers describe Quipu as the largest structure we can see today, they are being very precise. They are not claiming it is the largest structure that has ever existed. They are not claiming it is the largest structure possible. They are saying something much more careful. Within the limits of our current observations, within the regions of the universe we can map with confidence, Quipu is the largest confirmed structure we can identify. The name itself offers a clue to how scientists think about it. A quipu was an ancient Inca system of knotted cords used to record information, not by writing words, but by encoding relationships. Quipu, the cosmic structure, serves a similar role. It is not an object to be admired in isolation. It is a record of how matter has been distributed and connected across the universe. By mapping Quipu, astronomers are not just measuring size. They are reading a history written in gravity. This is why Quipu could not be discovered by simply taking deeper images. It does not announce itself visually. It does not glow as a single entity. Instead, it reveals itself only when many pieces of data are carefully combined. Positions, motions, and the physical properties of galaxy clusters. That is also why caution matters. Extraordinary size requires extraordinary care. Before scientists could describe something this vast, they needed to be sure they weren't being misled by perspective, coincidence, or incomplete data. Which leads naturally to the next question. If Quipu cannot be seen directly, if it cannot be photographed as a single object, how do astronomers know it is real? If Quipu cannot be seen as a single object, how can scientists be sure it actually exists? The answer begins with galaxy clusters. A galaxy cluster is not just a collection of galaxies. It is one of the most extreme environments in the universe. Between the galaxies inside a cluster lies enormous amounts of gas, heated to tens of millions of degrees. At those temperatures, gas doesn't glow softly like stars. It emits X-rays. This detail matters, because X-ray emitting gas does not appear unless gravity is strong enough to hold it in place. Without a deep gravitational well, that gas would simply drift away. So when astronomers detect intense X-ray emissions from a cluster, they know one thing for certain. There is real mass there, and real gravity holding it together. This is why X-rays are so important. Visible light can mislead. Galaxies can line up by chance along our line of sight. From Earth, unrelated objects can appear close together even when they are separated by vast distances. X-rays don't work that way. They trace physical conditions. They reveal hot gas trapped by gravity. They expose structures that cannot be explained by coincidence. When scientists studying Quipu examined the region in detail, they did not search for a dramatic shape. They searched for shared physical signals. They asked a careful set of questions. Do multiple galaxy clusters along the same filament emit X-rays consistent with deep gravitational wells? Do those clusters show similar motions through space? Do their positions and velocities align with predictions from large-scale structure models? Again and again, the answer was yes. Cluster after cluster showed the same signatures: hot gas, X-ray emission, consistent motion, not isolated points, but parts of the same gravitational system. This combination is crucial. Any single measurement could be misleading, but when gas temperature, X-ray emission, cluster motion, and spatial alignment all point in the same direction, coincidence becomes extremely unlikely. This is how astronomers distinguish between something that merely looks connected and something that is physically connected. Quipu passed that test. It was not confirmed by appearance, it was confirmed by physics. And this is what sets Quipu apart from earlier claims of the largest structure. Some past candidates were identified primarily by visual alignment or limited data. They were intriguing, but uncertain. Quipu's is different. Its confirmation relies on signals that directly trace gravity itself. Signals that don't care about perspective or viewing angle. In other words, X-rays don't lie about gravity. There is an important limitation to acknowledge. When scientists describe Quipu as the largest structure we can see today, they are not making a statement about the entire universe. They are making a statement about what can be measured and confirmed within our current observational reach. There may be structures just as large or larger beyond the regions we can reliably map. Science does not rule that out. But Quipu represents the largest structure whose coherence can be demonstrated using multiple, independent lines of evidence. That distinction matters, because science is not about making the biggest claim possible. It is about making the strongest claim that the data allows. And in that sense, Quipu is not speculative. It is conservative. It stands not because it sounds impressive, but because it survives careful scrutiny. Once a structure like this is confirmed, the focus shifts. The question is no longer just how big it is. It becomes something deeper. If the universe can organize matter on this scale, what does that tell us about the forces shaping it? Whenever a discovery sounds unusually large, a familiar question quickly follows. Does this break cosmology? At first glance, a structure like Quipu can feel unsettling. It stretches across a region of space so vast that it seems to challenge our expectations about how the universe should behave. But to understand why it doesn't break the rules, we first need to be clear about what those rules actually say. Modern cosmology rests on a simple but powerful assumption known as the cosmological principle. It states that on sufficiently large scales, the universe is homogeneous and isotropic. In other words, when viewed broadly enough, the universe looks the same in all directions and from all locations. This principle is often misunderstood. It does not claim that the universe is smooth everywhere. It does not say that matter must be evenly spread at every scale. In fact, the existence of galaxies, clusters, and filaments already tells us that the universe is highly structured on smaller scales. The real question has always been this: at what scale does that structure begin to average out? For decades, cosmologists have worked to identify the size beyond which the universe becomes statistically smooth. Not perfectly uniform, but uniform enough for the cosmological principle to hold. Quipu pushes directly against that boundary. It does not sit comfortably in the middle of our expectations. It lives near the edge. And that is exactly why it matters. Quipu provides something that simulations alone cannot. It offers real observational data at scales where the theory is hardest to test. It shows us how matter has actually organized itself, not how we expect it to behave in an idealized model. But size alone does not make something revolutionary. There is a crucial constraint that keeps Quipu grounded within existing cosmology. Gravity needs time. Large structures take longer to form than small ones. The larger the structure, the harder it is for gravity to assemble it within the age of the universe. Quipu's scale approaches that limit, but does not clearly exceed it. This places it in a narrow and valuable region, large enough to test our assumptions, not large enough to overturn them. That distinction is important, because science does not advance by discarding its foundations every time something unexpected appears. It advances by asking whether those foundations still hold under stress. So far, Quipu has not broken cosmology. Instead, it has highlighted where our models are most sensitive. It has shown us the scale at which homogeneity becomes a statistical statement rather than an obvious one. And that insight strengthens cosmology rather than weakening it. This is why astronomers are careful with their conclusions. They do not claim that Quipu proves existing models wrong. They say it tests their limits. More data will matter. Wider surveys, deeper observations. Only then can scientists determine whether Quipu represents an extreme but acceptable outcome, or a sign that refinements are needed. That cautious tone is not a weakness. It is the hallmark of a mature science. Big discoveries don't end theories. They refine them. And in this case, the refinement brings reassurance. The universe appears stable. Its large-scale behavior remains consistent. What Quipu offers is not a crisis, but a clearer picture of where structure fades into smoothness. To understand why structures like Quipu matter at all, we now need to shift perspective again. Not outward to even larger scales, but inward, not to individual galaxies, but to the environments where galaxies gather. To understand structures as large as Quipu, we need to zoom in, not to individual stars, not even to single galaxies, but to the places where galaxies gather. These places are called galaxy clusters. A galaxy cluster is a gravitationally bound collection of hundreds to thousands of galaxies, all moving within the same deep well of gravity. If galaxies are the basic homes of the universe, then clusters are its cities. Dense, crowded, active in ways that matter. Despite their size, collisions between galaxies inside clusters are rare. The distances are still enormous. Most interactions are slow, subtle, and shaped by gravity rather than direct impact. What makes clusters important is not just how many galaxies they contain, but where they sit in the cosmic web. Clusters form at the nodes, the intersections where multiple filaments meet. Matter flows along filaments, and over time, it settles into these nodes. That's why clusters grow so massive. They are collection points for both galaxies and gas. And environment matters. Galaxies living inside clusters tend to change over time. Star formation slows, gas is stripped away. Spiral shapes fade into quieter, older forms. Not because galaxies are fragile, but because their surroundings influence how they evolve. This is a key insight of modern astronomy. Galaxies don't evolve in isolation. Their fate is shaped by where they live. Most galaxies in the universe do not live alone. They live in clusters, embedded within larger structures like Quipu. Understanding these cosmic cities helps ground the scale of everything we've discussed. Quipu is not built from abstractions. It is built from real, physical environments, places where galaxies spend their entire lives. And yet, for all their visible stars and glowing galaxies, what truly holds these cities together isn't what we see. It's what fills the space between them. Inside a galaxy cluster, space is not empty. It may look dark and quiet, but between the galaxies lies something enormous. The space inside a cluster is filled with hot gas. Gas heated to tens of millions, sometimes nearly 100 million degrees. At those temperatures, atoms move so violently that the gas does not shine like stars. Instead, it emits X-rays. This glowing X-ray halo reveals something surprising. The hot gas inside a cluster often contains more mass than all the stars in all the galaxies combined. That means when we look at a cluster in visible light, we are seeing only a small fraction of what is actually there. This realization changed astronomy. For a long time, scientists assumed that stars dominated the mass of the universe. But clusters told a different story. Even after accounting for the hot gas, something was still missing. The galaxies were moving too fast. The gas was too hot to be held together by visible matter alone. This problem was noticed early. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster and found that its galaxies were moving as if far more mass were present than could be seen. He called this missing component dark matter. At the time, the idea was controversial, but decades of evidence followed. Today, we know that dark matter makes up the majority of a cluster's mass. It does not emit light. It does not absorb or reflect light. But it shapes gravity. Dark matter creates the deep gravitational well that holds the cluster together. It keeps the hot gas from escaping. It anchors the galaxies as they orbit within the cluster. In this sense, stars are only surface details. Gas and dark matter define the structure. This leads to a crucial insight. Light shows us where things shine. Mass shows us how the universe is built. The brightest parts of the universe are not where most of the mass is. And this is why X-rays and dark matter matter so much. They allow astronomers to trace the true architecture of clusters. Not just where galaxies appear, but where gravity actually dominates. When scientists study structures like Quipu, they are not mapping light. They are mapping mass. They are following the invisible framework that shapes everything we can see. Quipu is not impressive because it looks bright or dramatic. It is impressive because it represents a massive, coherent arrangement of matter, much of it unseen. Once you understand what galaxy clusters are truly made of, a new question naturally appears. If clusters are held together by invisible mass, what happens in the vast spaces between them? So far, we've talked about what connects the universe. filaments that stretch across space, clusters where galaxies gather, nodes where gravity concentrates matter. But this picture is incomplete without its opposite. Because the cosmic web is not just made of threads and knots, it is also defined by the vast spaces between them. These regions are called cosmic voids. A cosmic void is an area where the density of matter is extremely low, not zero, but far lower than average. Voids are not holes punched into the universe. They are regions where matter never gathered in the first place, or was slowly pulled away over time. And they are enormous. Some voids span tens of millions of light years. Others stretch across hundreds of millions of light years. At these scales, they become some of the largest individual features in the universe. To picture them, it helps to think in terms of sound rather than sight. If filaments and clusters are the notes in a cosmic melody, voids are the silences between them. They don't draw attention to themselves. But without them, the structure makes no sense. Physically, voids behave very differently from dense regions. Gravity inside a void is weaker. There is less mass to pull matter inward. Over time, matter tends to drift outward, toward the filaments and clusters at the edges. In that sense, voids slowly empty themselves. This outward flow is gentle, unhurried, but persistent over billions of years. Galaxies that form inside voids experience a very different life. They are isolated. They encounter fewer neighbors. They undergo fewer gravitational interactions. As a result, their evolution is slower and quieter. Star formation can continue longer. Disruptive events are rare. Environment matters here just as it does in clusters, but in the opposite way. This contrast reveals something essential. The universe is not shaped only by where matter gathers. It is also shaped by where matter does not gather. In fact, most of the universe's volume lies inside these quiet regions. That can be hard to accept. When we look up at the night sky, we see galaxies, stars, and glowing clouds. Our attention is naturally drawn to what shines. But light occupies only a small fraction of cosmic space. If we map the universe by volume rather than brightness, voids would dominate the picture. This is a crucial insight. If we focus only on galaxies, we miss most of the universe. We overlook the vast framework that gives structure meaning. Voids are not empty mistakes in an otherwise busy cosmos. They are a natural outcome of gravity working over immense time. They act as buffers, as regions of calm that allow structure to stand out. In this way, the universe is defined as much by what is missing as by what is present. The cosmic web is not overcrowded. It is spacious by design. And that spaciousness matters, because it brings us to an unavoidable realization. Everything we've discussed, filaments, clusters, and voids, exists within the limits of what we can observe. Beyond those limits, the universe continues. But our maps do not. And those quiet regions, stretching farther than light can easily reveal, lead us directly to the edge of observation itself. At this point in the story, it's important to draw a clear line, not in space, but in understanding. When astronomers talk about the largest structures we can see, they are not talking about the entire universe. They are talking about a specific region called the observable universe. The observable universe is not defined by distance alone. It is defined by time. It includes everything whose light has had enough time to reach Earth since the universe began. That detail matters. Because the universe is not static. It has been expanding for nearly 13.8 billion years. As space expands, distant regions are carried farther away. Some light can reach us, Some light never will. This means there are places in the universe whose signals are still traveling toward us, and others that are already beyond reach. The observable universe is the portion where light has arrived, or can arrive, given the age of the cosmos. Its radius is about 46.5 billion light-years. That number may sound strange at first. After all, the universe is only 13.8 billion years old. But expansion stretches space itself. While light was traveling, the universe kept growing. So the most distant objects we can observe today are much farther away than 13.8 billion light-years in present-day distance. Within this observable region, astronomers estimate there may be around 2 trillion galaxies. Each one contains billions of stars. Each one follows the same physical laws we measure locally. But this does not mean we are seeing everything. The observable universe is not the whole universe. It is simply the part that has had time to reveal itself. Beyond this horizon, the universe may continue. Perhaps infinitely, perhaps not. Science does not speculate freely here. It stays grounded in what can be tested. This is why language matters. When astronomers describe Quipu as the largest structure we can see today, they are being precise. They are not claiming it is the largest structure that exists. They are not making statements about regions beyond the observable horizon. They are describing the largest confirmed structure within the limits of observation. That distinction is not a technicality. It is the foundation of scientific honesty. Science does not grow stronger by pretending its reach is unlimited. It grows stronger by clearly stating where its reach ends. There may be structures beyond the observable universe that dwarf Quipu. There may be patterns we will never detect. But those possibilities remain outside measurement. And science does not draw conclusions from what it cannot test. This perspective often feels humbling. We like to imagine that better telescopes will eventually show us everything. But there is a deeper limit at work here. The universe is not hiding things from us. Light just hasn't had time. Time, not technology, is the ultimate boundary. Even with perfect instruments, some regions will remain forever unseen because their light will never arrive. Understanding this changes how we interpret size. Largest becomes a statement about context, not dominance. About reach, not finality. Within what we can observe, Quipu sits at the extreme edge of known structure. It represents how far gravity has organized matter within the window available to us. And that makes it remarkable. Not because it claims everything, but because it tells us exactly where our knowledge currently ends. Yet even within that boundary, the universe is not frozen. Structures evolve. Matter continues to move. Gravity keeps working. And that brings us to the final idea. Even inside the observable universe, the story is still unfolding. After everything we've explored, a quiet question naturally appears. What happens next? Not tomorrow, not in a million years, but on the longest scales the universe knows. To answer that, we need to introduce one final influence shaping the future of everything we've discussed. Dark energy. Dark energy is not a force you can point to in space. It doesn't clump. It doesn't form structures. Instead, it works everywhere at once. Its effect is subtle but steady. It causes the expansion of the universe to speed up. This wasn't always the case. Early in cosmic history, gravity dominated. Matter gathered, structures formed, filaments stretched, clusters grew. The cosmic web took shape. But as time passed, expansion slowly gained the upper hand. Today, the universe is not just expanding, it is expanding faster with time. This shift changes what is possible. Gravity can still hold stars together inside galaxies. It can still bind galaxies inside clusters. But across vast distances, hundreds of millions of light years, gravity begins to lose the race. Imagine trying to walk up a down escalator. At first, you can still make progress. But as the escalator speeds up, every step becomes less effective. Eventually, you stop gaining ground. That's what's happening to cosmic structure. The universe hasn't stopped forming structure because it ran out of material. It's slowing because expansion stretches space faster than gravity can pull matter together. Cosmologists sometimes describe this as a freezing out of structure, not freezing like ice, but freezing like motion, slowly settling. The largest structures, the ones we've been talking about, are likely already near their maximum extent. Filaments will not grow much longer. Clusters will not merge into vast superclusters spanning ever greater distances. Instead, existing structures gradually drift apart. This is the future of something like Quipu. Right now, its galaxy clusters are connected by gravity across immense distances. But over billions of years, those distances will grow. Not because Quipu breaks apart, but because space itself stretches between its parts. The links weaken. The connections fade. It's not an explosion. It's more like watching distant city lights slowly dim. Not because the lights go out, but because they move farther away. From inside any one cluster, nothing dramatic happens. Stars continue to form and die. Galaxies continue their slow internal evolution. Life, if it exists, notices nothing unusual. This is important. The future described by cosmology is not violent. It is quiet. There is no moment when everything suddenly changes. No cosmic alarm clock. Instead, the universe settles into isolation. Each large structure becomes its own island of matter, surrounded by ever-expanding space. To picture this, imagine a calm lake at dawn. Pebbles dropped long ago have already sent out their ripples. The water is now smooth. Nothing new disturbs the surface. The universe is moving toward that kind of calm. This perspective often feels counterintuitive. We tend to imagine the future as louder, bigger, more dramatic. But the universe seems to prefer stability. Its most active period, the era when the largest structures formed, is already behind us. That doesn't mean the universe is dying. It means it is settling. Stars will continue to shine for trillions of years. Galaxies will glow quietly in their local regions. What changes is not existence, but connection. This gives structures like Quipu a special place in cosmic history. They are not just large. They are timely. They represent the universe near the peak of its ability to organize matter across enormous distances. There may never again be a moment when structures larger than Quipu can form and remain connected, not because the universe ends, but because expansion gently prevents new connections from forming. In this way, Quipu is not a sign of instability. It is a sign of balance, a snapshot of the universe at a moment when gravity has done most of the work it ever will on the largest scales. And from here, the future unfolds slowly. The universe doesn't rush toward collapse. It doesn't explode outward in chaos. It simply continues, expanding, separating, letting distances grow. This realization carries an unexpected sense of calm. There is no cosmic emergency, no final act approaching. The universe is not in danger. It is patient. It has always favored gradual change over sudden endings. Understanding this doesn't make the universe feel colder. It makes it feel stable, reliable. And that stability leads us naturally to a final thought. If the universe itself is moving toward quiet separation, if even its largest structures are gently letting go, then there is no reason for urgency. No need to hurry. No need to keep up. And that brings us back to where we started. Not with the universe, but with you. By now, the universe may feel very large, not overwhelming, just vast. You've followed light across immense distances. You've seen how space stretches, how matter gathers, how gravity slowly shapes structure. You've seen that distance is also time, that looking outward is the same as looking into the past. And all of it happened without effort. Light did not hurry. Gravity did not rush. The universe did not ask to be understood. It simply continued. Every photon that reaches your eyes tonight began its journey long before you were here, before cities existed, before languages, before memory. And yet, it arrived, not because it was meant to, but because the universe allows time to pass. That quiet reliability is easy to overlook, but it matters, because it means nothing in the universe is waiting for you to keep up. Structures like Quipu stretch across hundreds of millions of light years. They connect regions of space that formed at different cosmic moments. Some parts of that structure came together before Earth existed. Others evolved while life was already here. From your point of view, it all appears at once, as if time folded itself into a single image. But the universe never experiences that image the way we do. It doesn't observe itself. It doesn't pause to reflect. It simply unfolds. Dark matter continues to hold structure together, whether it is noticed or not. Gas flows along filaments without needing names or explanations. Clusters age quietly, stars forming and fading on their own schedules. Nothing waits for attention. Nothing depends on awareness. The universe does not require understanding to remain stable. And that realization can be strangely comforting, because it means you don't have to hold everything in your mind. You don't need to remember sizes or distances. You don't need to track timelines or scales. There is no final test at the end of this story. The universe does not ask you to take anything with you. It will continue whether you are listening or not, whether you are awake or asleep. Right now, the most important things are much closer. The weight of your body, the surface supporting you, the slow rhythm of your breathing. These are not separate from the universe you've been hearing about. They are expressions of the same physical laws. The same gravity that shapes galaxy clusters also keeps you grounded. The same flow of time that stretches light across space also allows this moment to exist. Nothing is accelerating toward you. Nothing is collapsing behind you. There is no cosmic urgency. The universe is not counting down to anything. It has been here for billions of years, organizing itself slowly, patiently, without drama. It will continue long after this moment fades. And that doesn't demand awe. It offers permission. Permission to stop following the scale. Permission to let the vastness remain vast. You don't need to imagine the cosmic web anymore. You don't need to picture dark matter or distant filaments. Those things are already doing exactly what they need to do. They are not improved by attention. They do not speed up when observed. They do not slow down when forgotten. Like the tides rising and falling, whether anyone watches the shore. Like the earth turning, bringing night without asking permission. The universe moves on its own. And tonight, you don't need to move with it. There is nothing you are missing by resting, no insight slipping away, no understanding lost. The universe does not reward constant awareness. It allows rest. In fact, rest is part of how systems endure. Stars burn steadily because they are balanced. Galaxies persist because forces cancel and settle. Even the largest structures survive not through urgency, but through patience. And you are allowed the same. You don't need to keep pace with cosmic time. You don't need to stay alert to remain connected. You are already part of the story. Whether you listen or drift off, whether you remember or forget, the universe will continue to stretch. Structures will slowly separate. Light will keep traveling. And none of that requires effort from you. Tonight, the universe does not ask for understanding. It does not ask for attention. It asks for nothing at all. While galaxies move and clusters slowly drift apart, your only task, if it can even be called that, is to rest. You don't need to hold the universe together. It's doing just fine on its own. The universe has been here for billions of years. It will still be here when you wake up. Tonight, you don't need to follow it. You are safe. You can rest. Thank you for watching and for giving your time to explore the grandeur of the universe with me today. It's a privilege to share these discoveries with a community of curious minds. If this video changed the way you look at the night sky, please hit the like button and share your thoughts in the comments below. I read every single one of them. Until next time, keep looking up.